In the beginning, when God created the heavens and the earth was a formless void, and the darkness covered the face of the deep, while a wind from God swept over the face of the waters. He counted lots and lots of dust. This is End of Mission, the podcast where we preach to you about protein crystal growth and dust counting.
Welcome, my children. I know you are lost, but now you have been found.
Yes.
Let us talk about the evil ways of the secular and not godlike NASA.
I'm Paul, the pressure-fed astronaut.
Are we keeping that intro?
Yes, we are.
Oh, no.
Face of Sarcasm has been removed for medical reasons. He's been replaced with an AI chatbot.
Can't replace me.
It's exactly what the chatbot says. That's what I told it to.
Yay.
Okay. So on today's episode, we're covering Genesis. And like 5 pixels.
The great pixel shortage of whenever this mission was.
This is the early 2000s. This mission's about 20 years old.
Okay.
So
the great pixel shortage of 2004.
Well, yeah, you were going right. They were all being used in Afghanistan and Iraq. So yeah.
Oh, right.
Right. That mission accomplished banner needed a lot of pixels for that.
There's a lot of pixels for that one.
Okay. So we're doing Genesis, and Genesis is about solar wind. We're doing some dust collecting on this one.
Ooh, okay.
So, what is Genesis?
It's a device. You gotta do the intro from Star Trek 2.
So, Genesis is a device created by Dr. Cal Marcus for Starfleet to create habitable worlds out of dead ones. This is situated on the NASA research facility Regula 1, as seen in the documentary film Star Trek II: The Wrath of Khan. As you can see, the spacecraft's about 2 meters tall, Yeah. The launch vehicle is there. So Genesis is about solar wind.
Okay.
So this is a star, LL Orionis, right?
Ooh.
And you can see it's got a bow shock to it.
Yeah.
That's solar wind coming off of that star, hitting the interstellar medium.
And creating that bow shock.
Yeah. Which that looks really cool, doesn't it?
That is awesome.
It's very pretty. So the sun is constantly blowing off charged particles, right? Through the corona. Electrons, protons, morons, alpha particles, and trace elements. Carbon, nitrogen, oxygen, neon, magnesium, sulfur, iron. There's a lot more. From the original planetary nebula.
Mm-hmm.
It's particles.
Yeah.
You can catch them.
You can count them.
And you can count them. Genesis is born. So Genesis is the 5th Discovery-class mission, selected along Contour, the one that exploded. And this marks the first sample return mission done by NASA since Apollo 17.
Oh, wow. Okay.
Also the last solar wind sample mission also.
Wait, they collected solar wind on...
Yeah, they had a solar wind collector on Apollo. When we get to the Apollo program, they'll have it.
Mm-hmm. Oh.
Yeah.
Wow.
Now, technically speaking, Stardust was launched earlier, and that's a comet tail dust sample return mission, but that's coming back after this one.
So it doesn't count?
Yeah, it doesn't count. Technically, Genesis is first to come back.
Because it beat it back to the return. It's the return that matters, not the launch. Okay.
Oh, it definitely, that return definitely matters for this one.
Oh, no. Oh, no.
Discovery, faster, better, cheaper. Just remember that. So, Genesis is a very light spacecraft. It's a Discovery-class mission. It weighs 636 kilograms, or about 1,400 pounds, and it has about 142 kilograms of propellant, but 313 pounds. So it weighs a little more than I do.
Mm-hmm. Just a little more.
Yeah. So the goals of this mission... Wait, what's this? Okay. So the goals of this mission are... There's 3 of them. Obtain precise solar isotopic abundances of ions.
Collect a bunch of ions. Okay,
Yep.
get the bucket.
Obtain improved solar elemental abundances by a factor of 3 to 10.
Okay.
Because remember, most of the sample collection and what we know about it is from other spacecraft that are just hit by the stuff.
Mm-hmm.
This is actually collecting the dust and bringing it back.
Oh, so it's like when you drive down the road and all the kids are throwing rocks at you. You're now grabbing the bucket to collect all those rocks.
Yeah, now you're collecting them.
Got it. Okay.
And then provide a reservoir of solar matter for the 21st century.
Okay, that sounds awesome.
It's kind of like how we have like moon rocks that have never been opened or seen since the Apollo astronauts brought them back. Mm-hmm. It's like that.
It's like that. So we're packaging up all the solar dust into like a little container.
Yep. Yeah. So this is we'll see pictures of it. There's not many pictures of the spacecraft. There's not that many of it. There's no cameras on it. There's like 2 experiments not inside their sample return.
Okay.
So this will be accomplished by placing the spacecraft at Earth's Sun L1 for 22 months to collect solar wind.
Okay.
Now, there's 4 big plates of collector arrays here.
Mm-hmm.
And they're going to collect bulk solar wind. They're going to do specific events of solar wind, like coronal mass ejections, which are fast and slow. So there's solar wind that just comes off like normally, like every day. And then you have coronal mass ejections, which just throws stuff off. And there's a few types of those. And it collects samples from all of those. Because 22 months, you'll get all of them.
Right, okay.
And there's 2 onboard monitors. The electron monitor, which is this box here. And then there's a solar monitor, like here. That.
Another box.
Yeah. So we'll move the concentrator out to actually collect dust and solar particles. And then there's a concentrator here, which is looking for hydrogen. It repels hydrogen, but it collects the lighter elements.
Okay.
These collectors... So this is the sample return capsule. Sorry. I'm a bit scatterbrained still. So here's the sample return capsule. And it's going to dump it back on Earth, right?
Yeah, that's the whole point of a return capsule.
Yeah, so it's got canisters, drogue chutes, that fun stuff. And these are the collectors, all 5 pixels of them. I got this from the original Genesis website from 2005, okay? This is...
Oh, wow.
These pictures are over 20 years old.
Dang.
They're digital. So you can see they have these wafers on them. You can see how big the collectors are. So this is an actual collector.
Yeah.
And they're made of semiconductor-grade wafers, right?
Okay.
Kind of like on your computer.
Right.
It'd be very pure crystals. No dust or contaminants, right? Because you're collecting solar wind. You want to make sure you're collecting the correct stuff.
Right.
Why is there a French fry
of dirt
on
it?
Yeah. Yeah, why is there a French fry on this?
Oops. He pours like some ketchup onto it, dips it in.
Yeah, there we go. That looks nice. Get a little selfie with it, too.
Yeah. This is $200 million. Please leave.
Oops. So these collectors are made of different elements. The wafers are silicon, corundum, gold on sapphire, and diamond-like carbon films. So, for example, silicon on sapphire makes it easier to collect noble gases.
Oh, okay.
Yeah, so the particles will hit and get caught.
And so basically, that's why they have like these different colors, is because they're made of different materials to capture like different flavors.
Yeah, they're designed for specific, and to see different collection methods. Because you're going to be up there for 22 months, why not try out everything?
Right, okay.
So this is the spacecraft in assembly.
Okay, that's decently sized.
It's a cute little guy.
Yeah.
So you can see there's the big sample return capsule. Got the propellant tanks there, solar arrays, and then where's the electron detector? I think this is the electron detector there.
Or that little lump inside of the gold foil.
Yeah, what's there-ish. Again, there's 2 experiments on it. It's pretty flat.
Yeah, not much to it.
Yeah, so you can see how big it is compared to the Delta II that's carrying it up.
Wow, what a surprise. Delta?
It's a Discovery class mission on a Delta II. Wow.
Surprising.
Oh, look, Stardust. Right
yeah.
There. Yeah, the other sample return mission. That uses aerogel to capture comet dust.
Oh, not like these particular
No.
things. Oh, okay.
Because the solar particles are going a lot faster.
Oh, okay.
Yeah, a lot smaller and a lot faster.
Whereas the solar dust is bigger and slower.
Yeah.
Like
comet,
me.
Yeah, comet dust, yeah.
Yeah. What did I say?
You said solar dust.
Oh.
So here it is being loaded on the Delta II. Here's the Delta II on the pad.
Mm-hmm.
Okay, so it's going to launch on August 8th, 2001 at 1:13 p.m. Eastern Daylight Time.
Okay.
It's going on a Delta II.
Wow.
Exciting.
I didn't know that.
Yeah, exciting.
I never would have guessed.
And this one's got 3 boosters and a Star 37 because it's not, again, this thing weighs like 636 kilograms. It ain't that big.
It's small and light, and it's not going far.
It's going up to L1. It's not going that far.
Yeah.
Okay, so here it is launching.
Cool.
Yep. It goes to L1, so on November 16th, so a couple months later, it enters a Lissajous orbit. This one here. At L1, so the collectors open up on December 3rd, 2001, so 2 days after my birthday. And they're open for 850 days, collecting solar particles. So on April 1st, 2004, the collectors close. On the 22nd of April, Genesis maneuvers to go to L2, because they want to land on the day side of Earth. So they got to go all the way out to L2 and then come back.
Yeah, I got to do it in the day because otherwise, the contractors are going to get mad because they have to, get up late at night, collect it.
So you can see it.
You don't need to see anything.
They can actually catch it by helicopter.
Oh, really?
That's how they do this.
Oh.
Yeah.
Not a splashdown?
No. No, why would you do that?
Well, how would you do it by helicopter? If it's coming from above, it's the blades.
Well, it's got a parachute. It'll come in and snag it. We were doing this a bunch on the Corona capsule back in the 60s till the 80s.
Oh.
Yeah.
Oh. So we did just do helicopter catch.
Yeah. I have a video of this.
Oh.
You can see we're not that far into this, and we're already near the end of the flight.
Yeah.
There's a reason why.
Oh, no. Oh, no.
So it reaches L2 in July 2004. And then on September 8th, 2004, that's when it's going to hit the atmosphere and come back in.
Okay.
So 5.5 hours before atmospheric entry, the capsule separates from the bus of the spacecraft. And the bus itself will maneuver so it goes back to up to L1. Because why not?
So it's just going to stay up there.
Yeah, they do that with a bunch of these missions. Like OSIRIS-REx dumped its sample return, and then it's going off to another asteroid. Hayabusa 2 did that. It's off to another asteroid.
Oh. It's moving to a farm up orbit.
Yeah, it's going to another farm. Nice family.
Yeah.
So at 9:55 a.m., the sample return capsule hits the atmosphere over Oregon, aiming for Dugway Proving Ground in Utah.
Okay. Going over the West Coast?
Yep, so here it is. It's going to come in like this, get peak heating over Nevada, and then land at Dugway. So there's the Great Salt Lake. There's Salt Lake City there. To kind of give you a reference, right?
Right.
It's going to hit the atmosphere. It's going to come in. And it's going to, again, it's hitting the atmosphere at 11 kilometers a second, right? Boom, in.
Yeah.
Right?
Yeah.
And what's going to happen?
Fast.
So what's going to happen is a drogue chute's going to deploy, right? It's going to help slow it down, orient it, and it's going to help pull out a parafoil like that. And a helicopter is going to come in and catch it.
And snag it with a big stick it's got.
Yeah, it's got the big stick. And I have video of them testing this. So here's a test of this.
Okay.
There's no sound, don't worry.
Okay.
There it is.
Oh, wow.
It's really cool, isn't it?
Yeah.
Yeah. This is also how Rocket Lab was planning to catch electron boosters.
Huh.
Yeah, because they're small enough.
You could just do it with a helicopter.
Yeah. So now let's watch it actually happen.
Oh, okay.
I got video of this. This is cool.
Yay.
All these videos are in .vhs. I'm going to mute it. Pause for a second. I'm going to mute it. It's not recording sound, but it's got NASA commentary over it because it's NASA.
Oh, right. Okay.
So that little guy right there, that's the capsule.
That white dot in the blue sky?
Yep.
The
So it's
gray
coming
sky?
in. Here it comes. So this video is, 2 minutes long? Yeah. So watch this thing come on in.
Okay.
You excited? Solar wind. First
Yeah.
sample return since 1972.
When do the parachutes deploy?
That's a good question, though, isn't it?
Is it tumbling?
Yeah.
Why is... Uh-oh. Is it supposed to tumble?
Kind of. The parachute, again, that's what the drogue chute's for. It's going to pop open. It's going to help stabilize the vehicle.
Okay.
Here it comes. Sample
Still just-
return. Don't worry. It'll be fine. Here it comes.
It's getting bigger.
That it is. Because it's getting closer to the ground.
Yeah.
Yep.
I can see details of it.
Yep. Have you figured out why this mission's interesting yet?
Because the parachutes are deploying?
That's correct. Whee!
Oh, no.
All the way in. Here it comes. You can see it got scarred on the way in, too. Look at that.
Yeah.
That's pretty neat. It'll be fine. Don't worry. It's a little black
Video's
spot.
almost over.
Yeah, it's that little black spot where the parachute's supposed to come out. And there it goes.
Oh.
Oops.
NASA will say that it's a failed sample return mission, but we know the truth. It's aliens.
So this is where the parachutes are. Uh-oh. So what do you think happened?
Was it bolted in too tight?
No.
No?
No.
Did they remember... did they stage it correctly?
Sort of. So, have you ever heard of something called Murphy's Law?
Yes.
Can you say what it is?
Anything that can go wrong will go wrong.
Close. That's the popular interpretation of it. It's not the most accurate version. This actually comes from a guy named Major Edward A. Murphy, Jr.
Mm-hmm.
Now, this idea has been around since we could conceptualize anything that can go wrong will go wrong.
Mm-hmm.
He was born in January 1918, died in July 1990 because he's old.
Mm.
He was born in the Panama Canal Zone, actually.
Oh.
Yeah, again, 1918. Now, Murphy was an aerospace engineer who worked on rocket sled systems after World War II.
Okay.
So we did a bunch of to test ejection systems and to see if pilots can survive going fast.
Oh, right.
Yeah.
Okay.
Really cool stuff. Really interesting. There was the field of aerospace medicine was born because of this, and one of the guys actually said, well, if none of you are going to sit in this thing, I am.
Oh.
Really interesting stuff. But he was focused on safety critical systems. Because, you're putting people on these rocket sleds, they want to come back.
Right, you're trying to save them.
And after one accident, he came up with what's now known as Murphy's Law, which is if a part can be installed in more than one position, it will be incorrectly installed in the field.
Oh, okay.
Right? So right. You plug a switch in one way, it works. You plug it in the wrong way, it blows up. It's going to happen, right? You have to design it so that does not happen.
Right, that's why you have the color. You have color coded. That's why you have different sizes for the plugs and whatnot.
So how does this relate to Genesis? The error is here. You can see it. It's in this picture.
Okay, hang on a second. Okay, I can't see it.
It's in here. It's in there. Now, also, just take a good look at the spacecraft itself, though. Look at this. Isn't that cool?
It is really cool.
So you can see the different plates, and they just rotate into position to get solar wind.
Yeah, that's awesome.
It is really cool. You see the different wafer types. Got the cables and wires, and you can see how these things cost so much money.
Yeah, and then everything's wrapped in foils.
Yep. So it's actually right here. This is the thing that doesn't work. Can you see it?
Yeah, I mean, I could see the image.
Can you guess where this is?
This is, relay module. It's supposed to be... Well, you said that it was in the avionics box.
Yep, it's in the avionics box.
Okay.
So how does the drogue chute activate?
Is it because from an altimeter or accelerometer? Or
It's an accelerometer. So this is how this works. So two avionics boxes, right? Double up on everything in case one breaks. So you have 4 G switches which activate, and they'll send a signal to activate the drogue.
Okay.
That's what this is. So if you look closely, so this is like a systems diagram of it, and this is the actual circuit board, right? So these are the G switches right here, right? You see them?
Right. Yep, so those 2 G switches activate, and it deploys the chute.
Right. So this is the actual G switch they used, right? So you can see it's got this kind of a top to it and the rounded other end. And you accelerate this way, right? So what happens is see this pin in here, right? Got a spring.
Yeah.
So as it accelerates to 30 Gs, it'll activate.
it slides up into it. It needs to be 30 Gs to hit that to activate it.
And then it deactivates at 3 Gs, which that sends the signal to deploy the drogue chute.
Okay.
Right? So.
That's clever.
It's smart. So, right, as you can see, there's the top. These are the 2 G switches.
Yep.
Right? So you have to accelerate this way to make them work.
Right.
Which way do you think Genesis was accelerating?
The other way?
This way.
Oops.
They never accelerated.
Oh, gosh.
Murphy's Law, though.
If it can be installed in more than one way, it will be installed incorrectly.
This did it.
Wow.
Yep.
Okay.
So, Genesis hits the ground at 200 miles an hour because the accelerometers are installed the wrong way. You can find the volume 1 of the Mishap investigation report. It's linked in the description. It's very long. If you want to be a systems engineer, you get to write stuff like that. And they find some of these issues related to the crash. So, inadequate project and systems engineering management. Why are the accelerometers in backwards?
Yeah, how did you mess that up?
Inadequate systems engineering processes. How did you install the accelerometers in upside down? Inadequate review process. How did you not catch that the accelerometers were in upside down?
Yeah.
Unfounded confidence in heritage designs. You thought they weren't installed the wrong way. Failure to test as you fly. So pretty much it was a means of making sure that this worked no matter what. Like, as you're going, just kind of like activate it once in a while just to make sure. That there's no means of catching this until
it's screaming into the ground at 200 miles an hour.
Until it hits the ground at 200 miles an hour, yeah. And then, of course, faster, better, cheaper. They rushed the tests.
Yeah, I mean, this example just goes to show how important quality is, right? Quality control, quality checking.
Yeah, and that's here. That is the first 3 errors here. Because again, part of my job is I review things. I look for stuff like this. Mm-hmm. Like configuration management's a big one, but they didn't catch the fact that the accelerometers were in upside down.
Yeah, and that's part of my job too, is to review the designs of other people's work.
Yeah. And of course, you have Stardust coming in a few years.
Oh no, were those installed correctly?
They're fine. That one was fine.
Okay.
Don't worry. But yeah, again, faster, better, cheaper. Pick 2.
Yep, pick 2.
But all isn't lost. The capsule still hit the ground. I mean, there's significant damage, as you can see.
Right.
But it's not as bad as you think.
Are they performing an autopsy on this thing?
No. I wouldn't call it an autopsy. They're recovering it.
Oh.
Yeah. So here it is being pulled in, to be taken apart. You can see the different parts of the sample capsule.
I'm imagining they bring it into this room and then they say, "Show me," and it just fixes itself.
Oh, that'd be cool. Or I was thinking the emergency room scene in RoboCop.
Oh yeah,
like that. Yeah. So you can see it still does survive parts of it. They color code the remnants, right? Because you got silicon. I don't know what that is. Got aluminum oxides there. It's still actually kind of intact. They lose some wafers. They're broken, but
yeah,
they're intact. Again, they're in the capsule. They're in the shell.
Yeah.
So they start recovery and cleaning.
Oh. Okay.
So it hits the ground at 200 miles an hour into desert, which is dust. But most of the dust is actually up top here on the surface of the collectors, right? So these dark dots here are actual samples.
Okay.
So those are, nanometers, it's really small but
yeah,
there's a few that would penetrate more. But actually, most of the contaminants are pieces of the spacecraft and like grease and fluids because it's inside that.
Yeah.
So it's all isn't lost. Now you can find more papers on how they clean samples than you can of scientific results, as I discovered this week as I was working on the research. But you can see, so here's a sample of it, right? So on the top here is just a bunch of dirt and dust, and they clean it through selective cleaning washing processes.
Okay.
To clean up the samples, because again, you know what Utah is, and you know what vehicle fluids are. It's just getting rid of them.
Yeah.
Here's another one from that same paper. So this is the penetrant. This is the actual solar wind particle that hits.
Oh, okay.
And then up here is debris that they got rid of. You can see the outlines of it here.
Yeah.
Right. So the results are hard to read. They look like this. It's a lot. It's about isotope ratios because it's samples of solar wind. So you can see the rate. So result 1 is based on noble gas isotope findings compared to samples taken during Apollo 17. Solar wind composition has been the same for roughly the last 100 million years.
Okay.
So that's good. And you can see here the ratio of helium isotopes. So the bulk is 0 here, and then fast has higher helium-1 isotopes than slow helium. The 3 in slow it's different.
Oh, okay.
It's just a ratio.
Okay, I think okay.
Ratio of isotopes, right? You have the neon isotopes here, right? Fast, there's more of one. Slow, there's more of the other, and then the bulk is on average, somewhere around there.
Right. Okay.
Again, here's more results of like argon and different ratios. I don't understand what any of this is.
There's more of some stuff than other stuff.
It's solar wind. I was more focused on Murphy's Law.
Yeah, what Murphy's Law actually is.
The real reason this mission is interesting. So here's one. The sun has higher oxygen-16 isotope concentration than the rest of the solar system, so it's hoarding this.
Wow. It's the 1% of oxygen.
Let's get
16
isotopes. Let's get Space Bernie Sanders in here, and the 1%. They're hoarding all the oxygen-16. You can see there's like isotopes and how deep they got inside the sample. And you can see this is actually what they look like on the surface of the samples.
They look like boxes.
Yeah, little boxes. It's chemical reactions, I think. I don't understand what any of this is. I'm not a chemist.
Smacking into it and like leaving it does look like a little cartoon thing, when the character runs through the wall, leaves a perfect outline silhouette of him.
Yeah.
That's what's happening here. So elements and isotopes are all boxes. Confirmed.
Yep, there we go. It's not spheres or anything like that. It's boxes.
It's boxes.
That's right, Niels Bohr, I got you. So there's more oxygen-16 in the sun than there is in the rest of the solar system, which means something got rid of it from the original planetary nebula.
Okay.
There's 40% less nitrogen-15 in solar wind than in the terrestrial atmosphere. So we got more of nitrogen-15. We've been hoarding it.
We're the 1% for nitrogen-15 in the solar system.
Yep, that's right. We got you.
We got it.
That's right. You can see they only penetrate about 100 nanometers in.
Yeah.
Based on their speeds, so.
Wow.
This is another really short episode.
We're just cranking these out.
Yeah, they're really short. Again, it's not like ISEE3 where we have to go for 30 years and do space piracy to get these things. We did here, collected some samples and crashed.
Yes.
So, the spacecraft bus doesn't break or hit anything because it wasn't put in upside down. And it goes up to Earth's Sun L1 in November 2004, does a trajectory correction. They were hoping for an extended mission because it still has like a solar ion monitor, right? So you can monitor solar wind, but that doesn't come.
Oh.
So they put it to sleep on December 2nd, 2004, also after my birthday. So Genesis, while asleep, drifts out of L1 and goes into heliocentric orbit.
So it's orbiting the sun.
Where it is to this day, sleeping.
Soon to be awoken. Once again.
Yeah, we'll ISEE3 this thing.
It's still rare, right? The technology's only, 25 years old.
Yeah, we get our VHS tape player out.
Yeah.
Yeah.
Hey, if we can hack the planet,
we
can certainly hack space.
Yeah, space is easy. It's empty.
Yeah.
Yeah, Earth is all this dust. It's a solar wind that hit it at 200 miles an hour.
Yeah.
Now, you can go requisition samples from Genesis from Johnson Space Center to do analysis on them. Now, you and I can't do that because they'd say, well, you're podcasters who talk about fire a lot. We can't let you do this.
Yeah, you're a bunch of losers.
Yeah. So if you're a serious institution, you can fill out a form. I actually found the form you can get to get Genesis samples. Like, what wafer do you want? What are you looking for? How are you going to clean it? How are you make sure you don't screw this up?
So they're sending you the actual wafer.
You can get samples from Genesis, because that's how this works, right?
Oh, okay.
Yeah, you can actually get a sample of a wafer to go do analysis on it for solar wind studies, for whatever your purposes are.
Yeah.
You know?
Yeah.
So, despite the fact that it was put in backwards, a resounding success.
Yeah. Yeah, it still returned it, even though it...
Yep. Now, actually, on Osiris Rex, I remember this. There's the sample return from of asteroids with my name on it. They also had a drogue chute issue where it didn't open at the right time.
Ooh. Did it slam into the Utah desert at 200 miles an hour?
It didn't do that. But as we were watching it come in, I just remembered to myself, did they put the accelerometers in backwards? Yeah. That's Genesis. Faster, better, and cheaper.
Mm-hmm.
Wow, another half-hour episode.
Yeah.
Oh. Don't worry, STS-40, I'll spend 3 hours talking about medical science experiments. That's what I'll do.
Oh, thank you. Thank you.
Yeah.
I guess I now have to go back to church, find Jesus, and repent for my sins.
Yes. And thus saith the Lord, count dust, grow crystal.
Grow crystal, count dust.
Yep. Yep. I got my Bible. It's New International Version, which means I think I'm a heretic.
Yeah. We're both heretics.
That's heretics, yeah.
This episode is heresy.
Yeah, I mean, let's just read a little sample here. So this is James 2, my brothers and sisters, do you with your acts of favoritism really believe in our glorious Lord Jesus Christ? That's a good question, actually.
I do.
Well, no, God didn't save the mission.
Oh, yeah.
God's not a good systems engineer. What can I say? Murphy's Law, man.
Yeah.
So again, Genesis. It's not exactly that big. We're gonna take pictures of Mercury for 2 years. It's we collect some solar samples, crash, and then have
slam it into the.
Just throw it back.
We FedEx deliver it back to Earth.
Just drop kick it.
Yeah.
So our next episode is STS-40. We're doing some space lab sciences again. I did not pick it for that. I actually picked it for one of the gas cans. It's got floppy disks.
Ooh, wow. Look at that space age technology.
Yeah, fancy.
Floppy disks.
Yes, STS-40. That'll be a fun one.
Yeah.
So that's Genesis. Any final thoughts on Genesis?
Genesis? Watch Star Trek 3, The Search for Spock.
Also watch Wrath of Khan.
Start with Wrath of Khan, then watch Search for Spock, and then Voyage Home. It's a trilogy.
Yeah. Well, you should also watch The Motionless Picture, too. That's still good.
It is motionless.
Yeah, it is.
It is good.
Yeah, it's a bit more science-y than the other Star Trek films.
Well, it was trying to go for that slower pace of 2001: A Space Odyssey.
Yeah.
Which I don't think they remember that 2001: A Space Odyssey did not make money. I don't know why they.
I thought they did make money because stoners would go to watch the ending.
Yeah, they did eventually, right?
Oh.
They
once they finally realized that was there.
Yeah, well, they rebranded it to be 2001, the ultimate trip, right? And then you do drugs and then watch the ending of it.
That's true.
But it was a huge blow to Kubrick's career. His next movie was A Clockwork Orange, right? Imagine if Christopher Nolan made The Dark Knight, but it was not great, didn't make money, and then he turns around and made Memento.
Those are very good films, though.
Yeah, but one is way lower budget, right?
That is true.
He had to prove to Hollywood studios that he could make money.
A Clockwork Orange is a very good film, too.
It is.
It's very good. Again, it's Kubrick. He's good, but yeah.
Yeah.
We will cover 2001 as a movie at some point, and the book.
Yeah.
We will spend 3 hours talking about it.
Good.
And we'll just have really long slides.
We'll put it in the 2.35 aspect ratio.
Yeah. It'll be great. Genesis. Again, it's a fun little mission. And the next Discovery class mission near Shoemaker, we'll actually talk about what Discovery class missions are and how they came about, because near Shoemaker is the first. So we'll talk about that. Again, just fast, quick little episodes.
Yeah.
This is good.
This is good.
I don't know.
Maybe not.
I don't know.
It depends on the reaction, right?
Yeah. Well, again, with STS-94, we brought the shuttle back, took pictures, counted dust, lit some fires, came back. This
Burned
one,
the tires.
yeah, and this one, we went to a Halo orbit, collected samples and crashed.
Yeah. And then learned about Murphy's Law.
And we
what
learned
it actually is.
Yeah, and again, anything that can go wrong will go wrong is kind of an extension of that. You know,
But not really. It's specifically, hey, if you could put this in backwards, it's going to be put in backwards.
which that kind of goes to the that can go wrong will go wrong if you make it happen. So don't let that happen.
Don't let that happen. Make it very clear to the user
Yeah.
which way it's supposed to go in.
Yeah, like that one Proton launch where it takes off and it pitches over because the gyroscopes are in upside down, despite the fact that they're designed not to be put in upside down.
How did they put it in upside down?
There's a rumor it was sabotage.
Oh,
Yeah,
that's not good.
not good at all.
But how did design quality not check it? Or how did how did quality control not check it?
I think he may have been bribed with Pepsi.
Oh,
It's also
Classic.
It's Russian space flight post 2005 ish. Ain't so good.
ooh.
It's not so good. A lot of quality control issues going on because you have the whole collapse of the Soviet Union thing.
Mm-hmm.
Yeah. Yeah.
Oof.
But hey, Genesis. We collected some solar wind. We learned some interesting things about the sun, I think.
Yeah, it has. It's the 1% of oxygen 16 isotope.
Yeah. And STS-40 has 3 women on board.
Wow,
Yep. A record.
dang.
That's
How
good.
many people can it hold?
7.
Oh, all right,
Yeah. You can see there's 7 people on this mission.
right.
Yep. Genesis. Count dust,
Your planet,
throw it
welcome.
at the Earth 200 miles an hour.
All right. Well, this has been Genesis. It's a mission you know now.
Yep.
This has been End of Mission.